Here we have a model of Madison crater.
Yeah. Okay. So first thing, as we might say, so I've imported this data from a high-rise elevation data set. And you'll see if you download the data, you've got some of the elevation data as tiles. So the original elevation data set is much bigger. And this is just a tile that we've pulled out of it. There's also in here within the satellite images group, there is the satellite image of the area, right? So you've got both of those in the data set. The model that you've got here, when you've loaded it, the image that's used to texture this model is a much higher resolution image than the one that is in the model. The image that the full resolution image you can't visualize in one go. It needs to be split up. So what I've done that already, and it's put onto the individual tiles. So that processing can all be done in the software. And then in here we have the tiles. So I've got tile 1, 1, 1, 2, 2, 1, and 2, 2 displayed here. And you can switch these on and off individually.
So it's basically for people who also want to follow the this session, hands-on session.
Yeah.
So that's why we say the number of tiles. And also one comment about the data, all the data is open source, so you can just assess it. Ricardo, on the first day, Ricardo Pozzobon, he made a presentation about all the data sources. So this data is freely available, and you can just like go and explore any zone you would like to. And yeah, you can use this like as tiles. You can crop a certain section in QGIS and then export it to the VRGS. So any way works.
I'll just point out that in import, so if you right click on any of your objects, right, we have import item, and bottom right here, you go down to the bottom of the list, you see you have NASA high-rise in there as well as the data format. So you can bring your high-rise data straight in. So download the IMG file, and then that will go straight in. And the JP2 images will also go straight in. I think when you do this, you have to be aware that the JP2 files don't have embedded georeferencing information. You have to add it separately. And you can do that in the properties. And usually the georeferencing matches the IMG file, which does have the georeferencing embedded in it. So you can get your data together quite easily. All right, so we've got these different tiles. The first thing we're going to do is, well, it's scale is the first one. So how big is this thing? Let's stick one of our scale bars in. Let's put a scale bar up at this top corner here. And I'm going to do a scale bar. I'll put in just a standard scale bar, which isn't really very useful on this data set when we go in and look at it. So there's our 5 meter scale bar, but I'm going to change this. Let's do it at 50 meters, and let's do triaxial, and not so good because it's hiding. Let's then go into interpretations. I'm going to use this 3D translate function. So I've just gone to 3D translate, clicked on the scale bar. It's given me this widget, which allows you to then go in there and move the object in 3D. So we'll put it into, just move it so we can see it. And there's our scale bar now. It gives us a much better feeling. We should perhaps make the width a bit bigger.
Yeah, because with Mars it's especially important. Many processes, they have a completely different scale to what we are intuitively used to on Earth. So don't take it for granted. Please use the scale, because it's almost impossible to understand what is the size of certain landforms without it.
It's a very good point. And I'll add to that what I always tell people when they do an outcrop model or a picture like this, if you're going to put, say, something like this in a publication or in a presentation, and you put, right, I'll put a scale bar there, that is absolutely useless, right? Because that 5 meters is not the same. That measurement on the screen, so the number of pixels there is not the same over here. You should always put multiple scale bars in at different positions in your 3D model. So you take into help people understand the difference in the perspective. Right. So very good point that particularly like on this where you're not familiar with the scale of the data that you're working with. So always put scale bars in of the appropriate size. If you're going to use scale bars of different sizes, you use different colors, or that's my approach to it. So I always use red and yellow is 5 meters. So this one that I changed over here, I should really go in and give it some different colors to make sure that it's clear in the display that that is a different size to the ones that we've got down here. If ever you get lost, right click and do a go to, and it will take you to that object. Right? So anyway, there we go. Scales, always important. Right, the first thing we're going to do is let's go to different tile. No, I won't go there. Let's just pull it out here. Bedding measurements, right? Here, we've got some good places where we can possibly get some good bedding measurements and orientation measurements. So here's a very good one. It looks like we always have to be a little bit careful on data like this, is that when we've got these top surfaces, they might be a bit eroded. So hopefully what we're looking at here is the base of, certainly the base of a bed, remnant base of a bed. So we'll try and make a measurement there. So let's put an orientation in 1, 2, 3. Go to our charts, StereoNet, and there we've got a measurement on there. So now we can
And
try.
yeah, sorry for intervening again. And
Yeah.
maybe we can do a little bit like a very small explanation about the StereoNet for colleagues who are not geologists, for example.
Okay. So the
We
StereoNet, yeah. The
just a quick
StereoNet, what you're looking at, the way to think about it is that you're looking at, imagine a ball cut in half, and you're looking down on it from above. So if you were looking down on that ball from above, this would be the lowest part, and this would be around the equator of that ball, the circumference, right? And what you're then imagining is what these planes look like as they are cutting through that ball. And this line that you see is how that plane would cut that ball as if you're looking at it from above, right? And then you have these other points here, these called the poles to the plane. So this is a projection of where a line coming perpendicular out of that plane would also hit the ball. So it's a representation of the way in which it just gives you a visual representation of the orientations. The way to think about it, if the line is close to the edge, so the line could be round here or round here, that means the dips are very low. It's nearly flat. If your line is straight across the middle or cut straight across in a straight from side to side through the center, then that plane is vertical. And then you can think that you've got the whole range in between. So it's telling us about what the orientations is, but it allows you to compare orientations from different positions. So I've made an orientation measurement here. Let's go over here and do another one. So I could probably get a fairly good measurement going around here. So I'll do Let's try and do 1, 2, 3. And you can see those two planes, they're very similar on the stereo net. There's a little bit of difference, but generally speaking, they're quite close. And then when we look at them there, just use your look at them from different directions. You can see they're going in pretty much the same direction. Now we have some places where we've got some variability. Like let us talk about, well, let's try and do one more measurement. Let's see if we can do one over here, might be a good place. There we go. Again, a similar orientation. And then we can look, and yeah, things are mostly going the same direction, but here, now we can start to see there's some folding. These beds are not in the same orientation. When we look at them from different directions, they do look like there's a change in orientation. So let's put a measurement round on here and see what it comes out like. See if we've got any difference. So there is a bit of a difference there. It's a lower dip. Try another one. Let's do this one up here. So this is again where you're going through and you're using your geological expertise. So the dips have changed. So what the first ones we did were in this group. What we've just done here is in this group here. So you can see from the poles that they may be clustering in slightly different places. And what that is telling us, and we can actually see it in the data, that's what's probably happening, is we're going from steeper dips here, coming around this way, and you can see it when we look down. This is the great thing about working with data like this, compared to being in the field directly. You can just easily move your model around to look at it from different directions to work out what's going on. You know, in the field, you'd be like this, apart from you wouldn't see the disc. You know, that's where you would be, right? And you'd have, and that's what you would see on your stereo net if you were plotting it up in the field. But because we've got this kind of data, we can just zoom out and we say, okay, yeah, there you go. You can see that that's definitely a fold. So it's folding over here. And then we look carefully and say, well, what's going on here? It's coming down here. We're then going into this little valley. And there are some, and we've got some other features in here, but right over here, the orientations seem to be changing again. Let's do an orientation over here. We've steepened and we've gone steeper again. So let's look our back. What's happening? We've gone steeper beds over here. Comes over here, it shallows. They flatten off. We could even try, we might be able to get a measurement going around here. Let's see what that comes out like. I'm not entirely convinced of that measurement. Let's see whether we might be better off doing something.
Yeah, you should always take all the measurements critically. Like after you should rotate it, see if the surface is projecting interpolated in a correct way. Sometimes maybe the measurements that we receive, they are from the slope of the model. So we should be very careful with what we do. Just our hands extensions, because the brain is still here. Like software cannot do everything instead of you. So you should always analyze the results you receive.
So let's do another one like that. You see, even though you've got those two quite similar place, they're not far from one another. We're getting slightly different measurements, but I think from, I think they're representative. I wouldn't say they're 100% accurate. We have to bear in mind as well, we're working with elevation data, and there's been a lot of processing that's gone on in this data from physically the satellite capturing it through to it being this elevation data set that's on our screen. There's interpolations that have gone. There has been various processing that's gone. Quite often you lose the detail on the sharp corners. So detail like where we've got these breaks of slope going from the dipped surface to the eroded surface, you might get smoothing. So we have to be a little bit careful. But if we look at our model from a distance like this, and we use our intuition and we use our eyes and we think about what we're showing here, we can see that it's coming up, flattening off. They're not that far off from what we can see in the rest of the data. So not 100% confident, but they're representative. And what that is showing on the StereoNet here, so let's switch those on and off so we can see that these are actually, the dip direction has also changed. So they're quite flat still, but the actual direction in which they're dipping has changed. And that's what we can see in the data. We can see that in the model when we look at it, that we've got this change in direction, and then it goes back along here. You could spend a lot of time on this data set collecting lots and lots of these measurements and be able to map. So I could put one in here, for example, and it's a question of just huntering your way around the data set. And this is a really nice data set to work with because, all right, now that one there, I would say, I would go and look at that and say, perhaps that isn't as good as I thought it would be. It doesn't really seem to be matching up with the dip slope here. So I would maybe just get rid of that one and maybe put it in again or look for another place.
Yeah, we have just 15 minutes for this hands-on. Maybe we can
Okay.
also this.
All right. So there's another
Yeah.
2 more localities I want to show. That's the problem with these, that you can easily
Yeah,
get.
this data set is amazing. I want to just quit whatever I do in research now and just do measurements here because it looks so fun.
Yeah.
So
Right.
yeah.
So this is there's 2 more localities I want to show. Right. Now we've done bedding. Let's do faults. If we look, this area has loads of faults in it, right? We've got another fold coming through here. We've got possibly a fault running through here, but look along here. We've got all of these faults, which you can see, they're very clear. And what we might want to do is understand what the orientation of these faults are. Now, there's a really nice one. So I'm going to go into this bit. I put a waypoint so we can find where it is. And I'll come out. And as we zoom out, you can see a beautiful faults here. You'll see as well, you've got this funny overlap between the 2 meshes. And when I move, it changes its display. I've got an adaptive level of detail mesh running here. So when you're moving the model, while you're moving it, it drops to a slightly lower resolution to make, well, set up that way so people who are using lower powered computers should still be able to navigate around the model. And that's the overlap of the 2 tiles. So I set a small overlap when I generated it. But here we can see we've got this fault plane running through. And you can see the displacement on the beds here. And with a little bit of care, you can see that this bed here is probably this one. That's that one. That's that one. So we can see the displacement. We can see the trace of the fault. Let's take a polyline and we'll trace the fault as best we can, taking a bit of care. And there's our fault orientation in there. So we've managed to get an orientation off this fault. So it looks like we're So let's put this round to the north. So it looks like we are dipping quite steeply towards the east here. We could probably spend a little bit more time, put a bit more detail in it. So think about that from this sphere that we're looking at. Remember, we've got the looking down on this ball. Imagine it cut in half. And so this fault is dipping or going sort of progressively deeper into this direction. So that's what we've got there. So we've now got an orientation. Let's say what is the displacement on this fault? So how much movement has there been on it? I would spend a little bit more time working on making sure that I'm confident that this bed is that one, that bed is that one. You just need to double check, but let's just make an assumption we've gone from there to there. So we want to know what the displacement is on these, and there's a couple of ways that we can do it. So we can do we could just do very simply a measure vertical. So the vertical distance between there and there, and it'll be in the measurements here, comes in our properties. So this has given us a true vertical thickness. Well, it's telling us here we've got 2.79 meters. Now, that's not representative because we've got to take into account what the dip is in this area and account for that. So I'll try and do that very quickly. We'll put a measurement in. We've got a dip of 23 towards 184, and I'm going to add that in here. 23, 184. And then when I regenerate just re-click on the properties again, it's now telling us that the true vertical thickness, so that's just the difference in height, is 2.7 meters, but the true stratigraphic thickness, the corrected thickness, corrected displacement for that orientation is actually around 7 meters. So you'd have to think about projecting these lines up like this bed out like this, and it's the vertical perpendicular distance between those two beds that would give you the actual displacement. Right? You'd spend a little bit more time working on it. We're doing it quite quickly. Last one to look at is in, this is a really nice example. So another waypoint, but let's just zoom out on this. Is in here. Let's look at this in. Let's put some polylines in, or I'll do my interpretation of it. You can always go in and do your own. But what it looks like to me is that we have, let's put some polylines in. So I think we've got a fault that runs down like this. Certainly one there. Let's say, I think there's a fault running down like this. And I'm going to go, there's a fault running down, possibly somewhere through here. It might do down there. It's not particularly good. I think there might be like a displacement in the fault. And then, so yeah, possibly, is it that one? Let's say I think there might be one that runs,
I
could
think
be a
also
displacement there.
some problems in data here in projections.
So this is where we've got, got to think about the resolution that we're dealing with. And if we'd probably spend a bit more time working on this. Now let's put some polylines in. So I'm gonna actually just go into interpretations here. And let's get rid of that. I want to be, where are my polylines gone? So I've got these. I'm going to switch this to being my display style. I'm just keeping an eye on the timing here. I'm going to change my display style here to be a user. And I'm going to just quickly switch all of these. Because they're false, we should put them in red. Not always. So let's do that one. That one. And that one. Right, so now we've got those highlighted in red. And then we can try and start putting in some interpretations in here. So let's do a times polyline. So it looks like we've got there. And then we go there. And then are we looking at that one there? Maybe it is. There. I'm going to change my display style here. So I'm going to switch off the planes. I'm going to use a 3D trace. And I'm going to change my trace size to 1 meter. So it highlights it a bit easier. And then I shall do a few more. Let's just put one in there. I shan't bother changing the colors on these. So that seems to go all the way across there. And then, so I would then, obviously, as I'm doing this, I'm starting to see that there are problems with my initial fault interpretation. Maybe I got the wrong position on that. But really, what we're looking at here is that we've got variable displacement across these faults, and it looks like we've got basically a little set of rotated fault blocks. Now, you could spend quite a bit of time working on this. We've got, so with this part finishes at past, doesn't it? Just
Yes.
a little thing to show, which I discovered looking at the data earlier on this morning. Which I think is quite a nice feature to also think about, is that we're talking a lot about the geology, but we've got these dunes as well. We've got these beautiful dune structures. What we can do is we can use exactly the same tools to work out what the direction of migration is of these dunes. And we've got dip faces, we've got the lee side and the stoss side of these dunes exposed. It's actually quite difficult. The resolution of the data is just it's at the limit of being able to pull out the difference in the angles on the sides. But if we look at them, we might be able to start to see, but we can also, let's see, which have I done it? So I'll just go to tile 2. Is that the one with the big dunes in it? Yeah, tile 2 has got the big dunes in it. So I am going to run a thing called a tensor analysis. I should be tensor analysis very quickly. I'm going to use a 5 meters on this. This pulls out surface attributes, and I'm going to use orientation, coplanarity, and change of curvature. And there we go. We've generated an attribute, and I'm going to look at my dip map for these dunes. So this is the surface dip, and we can change the way this is displayed and get rid of high dips and just keep the low dips in there. So the bright colors are steeper, the darker colors are shallower. So that tells us that generally speaking on these dunes, we seem to have brighter values on this side, darker values on this side. So that suggests that when you look at it, you need to spend a bit of time. So maybe over here is easier to see. but that will suggest that that's the direction of migration is probably going in along this way. But you need to spend a bit more time working on it and looking in more detail. But they're right on the limit. Yeah, they're right on the limit of being able to pull the data out. Anyway, there you go. So a bit more time using the attributes as well. And you can see how the attributes help pull out the structure.
That's a
Should
way
we leave to that?
and the data. Yeah.
Yeah. So that kind of there, you can see the steeper sides on some of these, highlighting quite nicely. Cool. Anyway.
Okay. Well, thank you a lot, Susanna and David. We have a question from Alexandra. She says, such an useful software. Could you show, please, how to do georeferencing of a new data, please? And maybe I missed it. What is an example data for this high rise?
Well, the high-rise data here, the elevation data comes in georeferenced anyway. Very quickly, the way that you do it is, I won't run through the whole process. I'll just quickly show the approach. So you would do this thing in here, go to your mesh that you want to georeference. I'm just going to have this one switched on. And it doesn't matter what kind of data set you're working with. You do right click, make it active. And when you do that, you've got this extended menu of other things that you can do with your mesh. So this is really about processing the position of the mesh and doing some other stuff like the projective texturing, which we'll talk about later. Ground control points. We can add those in. So here you would do add tie point, not the tie point and target. That's for matching data sets to one another. So we'd put a tie point in there, and then you just do the same thing, GCP. Obviously, you put these in the correct position that you know of. And then down in here, the tie points in their properties, you have its position and its target position. So you would put in here where it's supposed to be. That's where it is. That's where it's supposed to be. This will be your error. And then you just quickly up here do corrections from ground control point. The more ground control points you put in, it'll give you a better estimate of the error in the referencing. So very quick to do. Works on all kinds of data.